Hello friends, I welcome you in lecture number 9 on higher order partial differential equations. In previous lecture we have seen the method for solving non-homogeneous linear partial differential equations with constant coefficients, and we have seen that to solve this type of non-homogeneous linear PDE, first we have to find out the solution of corresponding homogeneous differential equation, and that solution is called complementary function of this equation. After that we have to decide the particular solution or particular integral of this equation, and general solution is given by sum of complementary function and particular integral. And from this lecture onwards we are going to discuss shortcut methods for finding particular integral of this type of equation. Now shortcut methods are having their limitations. They are applicable for some special type of functions on the right hand side. So we are discussing different functions on the right hand side. For each type of special right hand side we have different shortcut method. So we will discuss this method. We will discuss shortcut methods for special right hand sides in this equation. So in this lecture we are going to discuss the method for solving this type of equation when right hand side is exponential function in this form, e to the power a into x plus b into y, where a and b are constants. And method is simple, as I have discussed in the previous lecture, that particular integral is equal to 1 divided by function of d dash, and here fxy is e raised to ax plus by. So whenever I have this type of exponential right hand side, then I will find out coefficient of x and coefficient of y in this ax plus by, and I will replace d by a and d dash by b in this function capital F. So I am putting d equal to a and d dash equal to b, where a is the coefficient of x here and b is the coefficient of y. And if this f of ab is non-zero, then this is our particular integral. If f of ab is non-zero, then particular integral is 1 over f of ab e to the power ax plus by. Now sometimes we may have f of ab equal to 0. So what will be the particular integral in that case? So for that, suppose f of ab becomes 0 after putting d equal to a and d dash equal to b. So in that case, here our function is f of d dash e raised to ax plus by, and suppose after putting d equal to a and d dash equal to b, this function f becomes 0. So in that case I have to differentiate this function f partially with respect to d, and then because this is function of d and d dash, this partial derivative is also function of d and d dash. So and whenever I differentiate, I will multiply by power of x, that is single power of x, because I am differentiating single time. If I am differentiating 2 times, I will multiply by x square, and then I will again check that after putting d equal to a and d dash equal to b, this remains non-zero. If after putting d equal to a and d dash equal to b, this quantity remains non-zero, that is first order partial derivative of capital F with respect to d at point AB remains non-zero, then this is going to be particular integral or particular solution. Now suppose this also becomes 0, then we will multiply by x square, and we will again take derivative of this with respect to d, and then again we will check whether second order derivative is non-zero at point AB. So this method is similar to the method for linear ODEs with constant coefficients. So here I have written first that when fxy is e raised to ax plus by, particular integral is 1 over f dd dash e raised to ax plus by equal to 1 over f of ab e raised to ax plus by if f of ab is non-zero. If f of ab equal to 0, then take derivative of capital F with respect to d and evaluate it at point AB. Suppose first order derivative of f with respect to d at AB is also non-zero, then particular integral equal to 1 x times 1 over value of this derivative at point AB e raised to ax plus by. Now suppose this is 0 and this is also 0, then we have to go for second order derivative. So if f of AB is 0, first order partial derivative of f with respect to d at AB is 0, and suppose second order partial derivative of capital F with respect to d at AB is non-zero, then particular integral is x square times 1 over value of this derivative e raised to ax plus by. So remember this formula for shortcut methods when right hand side is fxy, and using that formula we try to find out general solution of these equations. So here we can rewrite our equation as d square minus 2 times d dash plus d dash square z equal to e raised to x plus 2y, and I give this number 1. This is non-homogeneous due to presence of this function which is independent of z and its derivatives. So first I have to solve the corresponding homogeneous linear PDE. So I am writing that the corresponding homogeneous partial differential equation is, we consider right hand side equal to 0, d square minus 2 d dash plus d dash square z equal to 0. Now here we can observe that this is our function capital F of d and d dash, and we can see it is homogeneous. Degree of each term is same and it is 2. So we know that how to find out general solution of this type of homogeneous equation if f d dash is homogeneous. So for that we have to first write down the auxiliary equation. Auxiliary equation is written by replacing d by m and d dash by 1 in f d dash and equating to 0. So here I replace d by m, that is m square, minus 2, this is replaced by m, d dash by 1 plus d dash square, so this is also 1, m square minus 2m plus 1 equal to 0, and this I can rewrite as m minus 1 whole square equal to 0, and from this I obtain two values of m and they are equal, or we have the case of repeated and real roots. So therefore the general solution of equation 2 is nothing but complementary function of given equation, and we know that whenever f d dash is homogeneous we are writing arbitrary function of y plus mx. So first we write for m equal to 1, that is phi 1 of y plus 1 into x, that is x. For m equal to 1 again we have to write arbitrary function of y plus x denoted by phi 2, and here I have to multiply by x because I have two repeated roots. So this is the complementary function of given equation. Now for particular integral we have z equal to 1 over this quantity applied to e raised to x plus 2y. So now we try to write down the particular integral using shortcut method. Particular integral is 1 divided by d square minus 2 d dash plus d dash square, and function on the right hand side is exponential function e raised to x plus 2y. So here I am writing e raised to x plus 2y. Now if I compare with ax plus by, if I compare this x plus 2y with ax plus by, then I will have a equal to 1 and b equal to 2. And we know that if right hand side is exponential function, we replace d by a, here a is 1, and d dash is replaced by b, here b is 2. So first we try to find out this quantity for d equal to 1 and d dash equal to 2. So for d equal to 1 I have 1 square minus 2, d is 1 and d dash is 2, plus d dash is 2, that is 2 square e raised to x plus 2y. Here d is 1, that is coefficient of x, and d dash is coefficient of y, that is minus 2 1 2 plus 2 square. And we have to check whether this quantity is non-zero or not. So we can write one more step. This is 1 minus 2 into 2 4 plus 4 e raised to x plus 2y. So 4 will get cancelled, but we have non-zero quantity 1 over 1, that is e raised to x plus 2y. So this is the particular integral, and once we decide particular integral, we can easily write the general solution by adding complementary function and particular integral. Therefore the general solution of 1 is z equal to complementary function plus particular integral, and therefore z equal to arbitrary function of y plus x times another arbitrary function of y plus x, and right hand side is not right hand side, particular solution is e raised to x plus 2y, where this phi 1 and phi 2 are arbitrary functions, where phi 1 and phi 2 are arbitrary. So in this way we can easily find out the particular integral using shortcut method. All we have to remember is replace d by coefficient of x, d dash by coefficient of y, and check whether this fd dash remains non-zero. So here fd dash becomes 1 minus 4 plus 4, and fd dash becomes 1 at this point 1 comma 2. So therefore this is the particular solution or particular integral. We consider another example. Here our partial differential equation is of third order. Here partial derivative with respect to x 3 times minus 2 partial derivative with respect to x 2 times, and single partial derivative with respect to y. Similarly here we have d and d dash square plus 2d dash to the power 3 z equal to e raised to x plus y. Okay, let me check again. This is d cube minus 2d square d dash minus d dash square plus 2d dash cube z equal to e raised to x plus 1. So first we write down the general solution for corresponding homogeneous partial differential equation. The corresponding homogeneous partial differential equation is d cube minus 2 times d square times d dash minus d times d dash square plus 2 times d dash cube z equal to 0, and we have to decide general solution of this homogeneous equation. For that, first we observe that this function has degree same for each term, degree of each term is same, therefore this function is homogeneous. Here f of d dash is a homogeneous function of degree 3, and if f d dash is homogeneous, we can write the auxiliary equation by replacing d by m and d dash by 1. So here I am replacing d by m, that is m cube, here m square, d dash is replaced by 1 minus d by m plus 2, and equate this to 0. D is replaced by 1, d dash is replaced by 1, and d is replaced by m. And if we simplify this, we can take m square common here, and here we have m minus 2. Here we can take minus 1 common, and m minus 2 equal to 0. Therefore, again I can take m minus 2 common, and I am left with m square minus 1 equal to 0, and this gives me m square minus 1 can be written as m minus 1 times m plus 1 equal to 0, and therefore I have 3 values of m which are distinct, m equal to 2, 1 and minus 1, and therefore the complementary function is arbitrary function of y plus mx. First we take m equal to 2, another arbitrary function of y plus mx for m equal to 1, and third arbitrary function y plus mx for m equal to minus 1. This is the complementary function of given non-homogeneous linear PDE with constant coefficients. Now for particular integral, we have to consider f d dash on the right hand side and operate on the given function. F d dash is d cube minus 2 d square d dash. Let me write f d dash first. D cube minus 2 d square d dash minus d dash square, d cube minus 2 d square d dash minus d dash square plus 2 d dash cube plus 2 d dash to the power 3. And what is right hand side function? It is exponential function e to the power x plus y. So now because this is exponential function, I can apply that shortcut method. For that I have to put d equal to coefficient of x, which is 1, and d dash equal to 1, and I have to check whether this remains non-zero after putting these values. So let me first check. D is 1, d dash is also 1, so this is going to be 1 into 1. Here also I have 1 plus 2. So you can see 1 minus 1 0, 2 minus 2 0. That means this function of d and d dash becomes 0 if we put d equal to 1 and d dash equal to 1. So for that I have to multiply by x, and I have to differentiate this function with respect to d. Okay, we can write one more step. D by capital D is d cube minus 2 d square d dash minus d times d dash square plus 2 d dash to the power 3 e raised to x plus y. Because this becomes 0 for d equal to 1 and d dash equal to 1, we are multiplying by x and we are taking partial derivative, not ordinary derivative, partial derivative of f d dash with respect to d. So now what is derivative of d to the power 3? It is 3d square minus here 2 d dash as it is. Derivative of d square is 2d, that is we have minus 4d d dash minus d dash square. Derivative of d is 1 and plus 0. There is no d here and we are differentiating with respect to d, therefore we consider d dash as constant, and this is e to the power x plus y. Be careful while writing derivatives. This is minus 4d d dash minus d dash square. Now again we check for d equal to 1 and d dash equal to 1 whether this is non-zero or 0. If I take d and d dash equal to 1, here I have 3 minus 4 and minus 1, that is 3 minus 4 is minus 1 and minus 1 is minus 2. So this is non-zero for d equal to 1 and d dash equal to 1. So we consider it as it is. Here 3 into 1 minus 4 into 1 into 1 and minus 1 square, that is 1, e to the power x plus y. And this is nothing but one more step, 3 minus 4 minus 1 e to the power x plus y, and this is going to be minus 1 by 2. So finally we have minus x e raised to x plus y divided by 2 as the particular integral. And once we have particular integral, we can write general solution. Therefore the general solution of given equation is z equal to complementary function plus particular integral, and therefore z equal to arbitrary function of what was this sum CF, y plus 2x, y plus x, y minus x, y plus 2x, y plus x, and another arbitrary function of y minus x plus particular integral, which is minus x e raised to minus x by 2 e raised to x plus y. So we can see the power of shortcut methods. All we have to decide is that whether f of ab is non-zero. If it is 0, then whether first order partial derivative of f at point ab is non-zero, and we have to keep on checking for this non-zero derivative. And once we obtain non-zero value, we stop and we put d equal to a and d dash equal to b again. So in this way we can decide the general solution of non-homogeneous linear PDE with constant coefficients if right hand side function is e to the power ax plus by, and we will remember that particular integral is given by replacing d by a, d dash by b in FDD dash, provided f of ab is non-zero. If f of ab is 0, then we differentiate capital F partially with respect to d, and again we replace d by a, d dash by b in this partial derivative, and if it is non-zero, then we multiply by x and we write down that non-zero value of partial derivative and e raised to ax plus by. This is going to be particular integral. So in this lecture we have discussed that how to find out the general solution of non-homogeneous linear PDE with constant coefficients, and if right hand side is an exponential function. In upcoming lecture we will consider different right hand sides of this type, and we will see the different shortcut methods for finding general solution of this type of non-homogeneous equations. So I stop here. Thanks for watching.